and welcome to the LOF&BE webinar. That's October edition. And I'm Sayaka Sorozuki from National Research Institute of Fire and Disaster Japan. And this is hosted along with Sarah Macarista from US Forest Service and Samuel Mancero from NEST. And today's speaker is Enrico Ronchi, and he is associate professor at Lund University, Sweden. He is recognized for his numerous research contributions that have covered a wide range of areas concerning human behavior in fire and fire evacuation. He is also actively involved in teaching activities in the fire safety domain and being responsible at Lund University for the International Master of Fire Safety Engineering program, arranged with Ghent University and University of Edinburgh. His work has been published in more than 150 publications, including more than 60 peer-reviewed journal articles, commenting in prestigious journals such as Nature. He is currently associate editor for the journals Fire Technology and Safety Science, and a member of the editorial board of Fire Safety Journal and the European magazine of SFBE. He has also translated his work into practice through his involvement with multiple committees and publications with ISO, SFB, Italian, US, and Swedish governmental organizations. So, floor is yours, Enrico.
Thanks a lot, Sayaka, for the nice introduction, and welcome everyone to this webinar. So today I will talk about evacuation modeling for wild and urban interface fires. So what I will do is I will give a general overview on the latest research efforts done in this domain, and give a general context of what is the state of the art of evacuation modeling tools for WUI fires. So to start, I will give some background on why are we even looking at the use of evacuation models for WUI fires, because I will say that historically there is quite some difference in terms of usage of these tools for a WUI fire domain compared, for instance, to the building fire domain, in which there is historically much more use of those tools in engineering practice. But I will explain also why this is important in this other domain, and also going into the different layers that can affect the evacuation process. So seeing what are the different components, modeling components that can play a role into evacuation, and also how they need to be integrated in order to produce credible results. These are very important aspects, because we will see, and I will give an overview on this as well, that there are different approaches that may rely or not on implicit versus explicit representation of certain behavior and certain aspect of the evacuation process. So we want to understand how this is solved, what is modeled implicitly or explicitly, and what are the possible approaches in there. And this will be done also for the different modeling components. So we will look at the key aspects affecting evacuation, so the impact of the wildfire itself on the evacuation process, both when it comes to representing evacuation response or also the actual traffic response. And this means that we will look both at the pedestrian component, so the response of each individual, but also then once those individuals go into their vehicles, how this would impact the flows on the traffic network. So looking more at the larger scale, so from households to road network level. And then I will make an example of a tool, that platform that we have been developing for a couple of years. This is an international effort that has been sponsored by NIST across different projects. And this tool is called Winity, and it is called Winity because it is indeed developed in Unity, that is a game engine. And it has the goal indeed to integrate different modeling layers. So to have a wildfire model talking to a pedestrian response and a pedestrian movement model, as well as a traffic model. So this is one example of a tool that is available for doing indeed evacuation modeling. And we will see how those type of tools work, what kind of outputs they can provide, and also what is the practical use, potential practical use in real life when we deal with evacuation planning or real-time emergency management. So my conclusion will be focused mostly on what is the benefits of using this type of tools indeed, and why we should move away from just looking at an assessment of fire risk and vulnerability of a community purely based on the, let's say, fire-related aspect of it, but it's important to integrate also other aspects in the picture which are related indeed to the ability of the community to respond to a wildfire event. So that's where evacuation models play an important role. So this is a bit the outline of what we will talk today. And the first big question that I have is, why do we actually want to use evacuation modeling for wildfires? Because this is something that is pretty well established, as I mentioned before, in the building fire domain, where we often use evacuation simulation tools for performance-based design, or we use them to identify possible design faults when it comes to the analysis of bottlenecks that could be popping up from a specific building design. But instead, it's not as straightforward when it comes to fire evacuation. So the starting point is that at the moment, when we look at a wildfire evacuation, or even more specifically on a wild and urban interface fire evacuation, often the very only source that we have to identify the possible scenarios and plan the response of the community is the knowledge that we have from previous events. But this brings quite a few problems because there is no guarantee that whatever happened before will happen in the same way, with the same scale afterwards, when there is a next disaster. And I mean, I come from Lund University in Sweden, where we're really seeing this firsthand, because in 2018 we had a particularly bad year when it comes to wildfires, which meant that we have a completely unprecedented scenario in which we had several wildfires all over the country, and this brought a lot of issues when it comes to be possible to refer to previous experience, because we didn't have a scenario like that before. And I mean, we could talk about a lot about why and this happens, and I mean, I'm sure there are a lot of people in our IFSS research community that are more qualified than me to talk about this, but some of the obvious factors are linked to both climate change and also increased urbanization next to the forest, something that we see more and more happening all over the world. So what happened is that it is sometimes difficult to assess the impact of a given decision along the incident timeline. When it comes to evacuation planning, sometimes it is crucial to give an evacuation order at the right time, because we all know that on one hand, it's important to make sure that people reach a safe place on time. On the other hand, unnecessary evacuation costs a lot of money. So both for disruption of activities and so on, but they also have some inner costs associated with that. So as I said, it's very important to evaluate carefully what kind of evacuation order we give and when. But again, it's very hard to predict then what will be the impact of certain decisions along the incident timeline. So we need more data to understand what is the impact of certain decisions, but even more important, we need more predictive capabilities. So we basically need to evaluate what are down the line the impacts of certain decisions on the incident timeline. And As I mentioned before, authorities can have different approaches and they take different decisions when it comes to emergency management strategies in case of wildfires. And we see that worldwide there is quite some also inconsistency across different countries. Sometimes we even find inconsistencies within the same country with different states that have different let's say provisions related to the actions linked to wildfire and wildfire threats. So what are the possible scenarios? Well, we may have a mandatory evacuations in which everyone is actually told to leave the endangered area. We may have recommended evacuation, so it's not a mandatory command that comes from an authority. Stay or go, so another policy which implies staying or deciding to leave early, basically, or stay and defend, which means to basically remain in the threatened area, or even voluntary evacuation. There may be situation in which people actually on their own decide to leave a threatened area. At some point, I think there was it was all over Twitter and all over the news. We even have what can be called preventive evacuation. So when it was assessed there was a very high risk in some areas, it was actually a trigger by the let's say by this assessment to leave the area anyway. But and again, this happens especially in countries or states that have not had so far so much experience with wildfires, even lack of policy. So there is not really a coordinated policy decided upfront concerning what to do in different situations. And this can create, as you can imagine, many issues when there is a real event. And again, this depends a lot and varies a lot from the experience of that given area with wildfires, thinking that this could range from places where this is really part of the daily life of people, thinking about Australia or California and so on, to parts where this is actually a new problem. And I think about where I am based, like Northern Europe, where a lot of authorities and stakeholders are waking up to this problem as something new. So all in all, authorities' instructions may change over time, which means that we need to be able to understand rapidly what is the impact of the changing conditions on the outcome of an evacuation and the outcome of a wildfire scenario when it comes to life safety. And here, to make you understand the complexity that can be associated with wildfire events, is an example of a set of timelines which could be used to represent an evacuation process. And this is definitely not the only possible timeline. There are several possible sequence of events that can occur. But as you can see, even looking at one specific area, it can get quite complex because we start with ignition, then we may have background traffic already on the road. Some people, they will decide to stay regardless of the evolution of the event, even despite they've been told to evacuate, for instance. And then we have a given evacuation response, so with different households in different times deciding to respond and leave the threatened area. And we have evacuation that can take place on the road network. And at the same time, we may have people that have to travel to reach their vehicles, or sometimes it's even not as simple as just people reaching their vehicles and going towards a shelter or a safe place, but it might indeed include a set of activities that people will do, for instance, to fetch family members and so on. So it's really not straightforward to understand the timelines of wildfire evacuation, and those are linked also to possible events that might affect also to a large extent the outcome of an evacuation proceedings. Let's think about, for instance, the loss of a route due to the evolution of the wildfires, or shelter loss due to the fire. And those are all scenarios that happen in real life. So this is not theoretical things, it's things that happen. Or actions done in the traffic management side, like lane reversal, so decided to swap lane directions in order to increase capacity of a given road, or even accidents. And that we know from the traffic safety literature that it can have repercussion of the whole on the whole road network when we have an accident along a link in a road network. So all in all, this is quite complex, and we are ourselves in the situation to try to use these timelines to interpret the sequence of events, and that's where simulators come handy, because they can help us figure out how possible single events or a sequence of events can actually have an impact on those timelines. So what is generally done at the moment is indeed to try to model the different modeling layers and see what are the interplays between the different variables within them. So why this is getting more and more interesting, because we are gradually going towards the engineering of WUI design. So basically mirroring the approach that we have been used so far in building fires, we are actually moving towards doing the same in the WUI domain. And we have seen this getting more and more popular. There are more and more people looking at this approach. We actually saw this in one of the latest webinars. One of the colleagues, a researcher, Emanuele Gissi, that was giving his presentation, indeed quoted this approach as a valuable approach. And we see more and more in the literature. There were some research in Australia also looking into this. So basically, trying to make use of the traditional concept that we have in performance-based design of buildings, but for WUI fire, so to a much larger scales. So how this works, basically we evaluate the available safe egress time due to the wildfire, and we compare it with the required time for egress, and we make sure that people reach a safe place with a due safety margin. The situation, though, is much more complex than what we have in a building, because apart from the temporal scales that are much larger, but also the spatial scale are not as clear as when we are in a building, because the building is pretty much a confined space in which we have we know more or less where are the contours of the space that we need to look at. Instead, when we look at wildfires, very often we come in the situation that we are not really sure about what is going to be the area of interest from the beginning, because we might have different factors that influence this area, may make it larger for due to the wildfire spread and evolution of the wildfire. So again, this gets much more complex, and even the type of timelines that we used can get also quite more sophisticated. Indeed, these are a couple of examples, for instance, of A set and R set and WA set and WR set timelines that we can have. But we can see that starting from ignition, there are many things that can happen from the time of ignition to the actual tenability limit reach. So that entails indeed the understanding of the incident detection, notification, what is called pre-evacuation, so the time for people to respond and movement. But again, it can get much more complex when we put in the picture also the firefighting actions and intervention, and how this affect indeed the spread of the wildfire, what kind of notification we use, if it's a public notification or not. And again, even the mode of transport can be very different, because we could have indeed both people using their private vehicles or using public transport, or in some instances we even had cases of people evacuating on foot or even via boats, given the particular configuration of an area. I mean, there were a couple of real events in which we were really cutting out the main road out of a given community, which means that the only way out, being those communities on the coast, was via the sea. So again, there are a lot of complexities linked to the design of safety for WUI fires, but the general principle is that this WA set, WR set concept can be used anyway. But to do so, along with the more classic tools that we use for the assessment of the threat, we need to have tools also able to understand how it works, how the evacuation works. So how the evacuation process works. And as mentioned before, we may find ourselves dealing with a lot of different interactions between different modeling layers. So starting from the fire modeling, which is something that we see more and more consolidated in the literature, because I will argue that wildfire modeling has been around for wildfires for much longer than evacuation modeling. Because I mean, traffic evacuation models existed also for quite some time, but the ones that are available on the market, the majority of them, they were mostly designed originally for normal operations or for other type of evacuation threats. Think about hurricanes or tornadoes and so on. So it's relatively new, the field that is looking at the application of large scale evacuation models for the domain of wildfires. And this means that we cannot just look at one specific component at a time. So we cannot just look at the traffic modeling layer, but we need to also look at the response of people, and we need to use possibly also dedicated models to understand the response of people, the movement of people, their access to the vehicles, their access to public transport, and so on. So it's as I say, it's a problem quite complex, which requires different modeling layers to be represented. And we also have to take into account that those modeling layers are not completely independent from each other, so they will actually affect each other, and they have to be integrated, because we will see certain outputs from a given set of models may actually have an impact down the line on another modeling layer. So the main core components that we want to represent when we study evacuation with simulators is, of course, the fire component, mostly to check what is the spatial and temporal evolution of the threat, which in turn has actually an impact on the network availability. But this is just an example, the road network availability, but this can have an impact on several other things, like indeed the pedestrian response, the household level, or even the availability of the what are the designated destinations. Think about shelters and so on. Then we need to represent the pedestrians, so people, and to do so, we need to make an assessment of what population we're dealing with and check what is the evacuation time within a given building or area. So we jump, let's say, from a more local understanding of what is happening in a given infrastructure to then scale it up to a whole community. And this can be used as an input for traffic models, because they help us understand what is the traffic departure time. And then we go into traffic modeling layers in which we actually look at vehicle demand. So we see basically what is the travel demand, what is the capacity of the road network, and management, traffic management solution that may impact this road network capacity, because we should not forget again that there may be some actions from authorities that can be helpful to increase the road capacity. As I mentioned before, think about aspects like lane reversal and so on. Route choice, so how people pick their route, and there are many variables that play an important role there. Familiarity, evolution of the threat, and so on, and availability, because as mentioned, there may be accidents, road accidents that may impact availability, or there may be actually smoke along the road, and there may be the wildfire itself that may make certain parts of the road network not available. So those are the three key modeling layers that we're looking at when we deal with evacuation modeling for wildfires. They're not the only ones, because there are other aspects that we may want to take into account as well. But I would say that these are the key ones. Of course, there are many other variables and layers that implicitly or explicitly can be represented and that have a specific impact on some of these modeling layers. Think about, for instance, firefighting efforts is one clear example, or weather, and so on. But as I said, these are the key main aspects to put into an evacuation modeling platform to be used for wildfire, for the assessment of a wildfire consequences when it comes to evacuation in the WUI. So as mentioned before, those are not layers that can be treated in isolation. So you cannot really just run one at a time and expect that those will function, will give a realistic results just by running them in sequence. But in reality, we need to make sure that the outputs of certain models, modeling layers, they actually do affect the other modeling layers. And here I make some examples. For instance, think about how the wildfire threat can impact pedestrians in terms, for instance, of affecting their response. So their pre-evacuation response at the household level, or even on the traffic, availability of routes, availability of shelters, and so on. Pedestrian models that could be used actually to load the road network. So that's actually the output from those models can become inputs for a traffic model. And the same traffic model can also have an impact backwards on the wildfires, because for instance we could through a traffic modeling layer we could assess how much land firefighting how much time land firefighting needs to get on the scene. So a fully integration will allow also to assess that. Or, since I explained before, people do not necessarily go from their home to the safe place, but they may be located somewhere else. They may be located at work. They may be fetch other people. So even the traffic layer could be used to have an impact on the pedestrian response and so on. And as mentioned, there are many other layers that could have an impact on those sync models, or the models that read those outputs and put it as inputs. But this is just an idea for giving you a picture of how those layers are very much linked to each other. And also in these graphs that I put here, this come from a project that we did for NIST a couple of years ago, the e-Sanctuary project, in which we also did a crude evaluation of the temporal scale / computational time versus spatial scale, depending on the type of modeling approach that we use. So how much room we have to use a more sophisticated or a more simplified approach for the different layers in relation to the type of scale that we deal with. Because again, if we are using something for real-time emergency management, we may not afford to use very sophisticated models which require a higher computational time, unless we have some sort of pre-calculated scenarios, while instead we may opt for a more macroscopic approach or empirical approaches, simpler approaches, and this gives us an idea on what are also the limitations of the computational power that we have nowadays on how to use different type of modeling approaches. So, concluding this part on the motivation of the work, basically we need to have integration of modeling layers. And not only, because until a couple of years ago, what we often found in the literature was that you could get hold of some models that were able to represent some of these aspects that we discussed, or at least in a very simplified way, at least some of those aspects. But the problem was that sometimes they often came either from somebody that he was an expert in one of those areas that put together a plugin to also address another area. So okay, I'm a traffic modeler, and I represent a very crude impact of the wildfire, but I'm not really into that field, so I don't really know exactly what I should put in. Or vice versa, I'm an expert wildfire modeling. Oh, I should also take into account of evacuation, so I put something there. So that's the problem. Those modeling layers have to be addressed with a consistent level of granularity. And also, it's important to understand what is the most suitable modeling approach depending on the scope of what we are doing. Because again, if we use those tools for planning, it's not the same that if we use them for real-time incident response, because the computational constraints are much higher in the latter case. And we have also different approaches available, which, as mentioned, can focus on representing certain layers implicitly or explicitly. So either within an existing model, you represent also implicitly the impact of a given modeling layer, or explicitly you have a dedicated model that addresses that. And here I make an example of how we can represent wildfire evacuation with modeling tools. This comes from the chapter of the encyclopedia that actually Sam was editor for, and myself and Steve Gwynn wrote a chapter indeed on computational evacuation models for water and interface fires. And what we looked at was indeed what are the options available nowadays for representing evacuation. So the first approach is, okay, I have a fire model that is run, and then I have an explicit representation of people response people movement, so people response, I mean here the pre-vacation time. So how long do you take to respond to the event when you are, for instance, your household? People movement, how long it takes for you once you've taken a decision to leave to reach a vehicle. It can be your private vehicle or public transport and so on. And then we have the traffic modeling layer, which actually does the simulation of the actual movement along the road network. And approach 2, this is, so the first one is everything is explicitly modeled with dedicated sub-models for each of those. The approach 2 is that once we have a fire modeling representation, we have a people response that is implicitly modeled. So we have a representation of people movement modeling, and this includes already a representation of people response. So it's already implemented within that model, the response of people. And this then becomes an output that is used by the traffic models for representing the movement along the road network. So this is a bit less detailed representation of the behavior in this case that we will see. So generally you will have, for instance, some sort of a distribution of possible responses that is implemented within the people movement model. The third one, instead, is an approach that starts from the fire modeling and then put everything inside the traffic modeling layer. So you implicitly reproduce both people response and people movement by just adding a given time delay to the traffic modeling layer. And this, I would say that this is the approach that we have seen widely used until not so long ago. I would say 5 to 10 years ago. The majority of people that have looked into this problem, they were mostly coming from the traffic modeling domain, and they were familiar with this type of model, so they were not people necessarily expert in pedestrian modeling. So you often see this represented at the more aggregate level. So you would just have a response curve that was used to calibrate then the travel demand inside the traffic model. So that's a bit the different possibilities that we have nowadays. Of course, we go back to the trade-off between the different needs that we have. It may be that we need to do some calculation quicker, so maybe we cannot reproduce everything explicitly. On the other hand, some aspect may be important for our specific situation. Like think about a scenario in which not all evacuation happens along the traffic road. Then you need a pedestrian movement model if you don't have that kind of scenario. So these are the approaches that we have available nowadays. And now let's go approach like modeling layer by modeling a layer to see what approaches can be used and what are the factors that play a role in deciding what approach to use. Because when it comes to fire modeling layers and they're used for evacuation modeling applications for wildfires, the fire outputs can be either sourced from external or an internal model. So basically you can either rely on outputs generated by an external model. So you take an existing wildfire model and you fetch the outputs from that and you import it into an evacuation model to see the integration of those with the other modeling layers. Or you can build your own internal model within your tool that allows you internally to represent the wildfire spread evolution. But what are the problems here? First of all, if you develop a new tool, probably it's going to be less familiar to the user. So it's important to evaluate what are the consolidated uses or users of a given modeling approach. Then if you import something from an external model, you will have to rely on the development done by that model developer in a way. So if something changes there in the way outputs are exported, you will have to change your code to fit it with whatever has been changed the other way. One important aspect though, that if you rely purely on an external model, so if you take an empirical or physics-based model and you import the outputs into your model, you're not allowed to do two-way coupling directly within your tool, because you basically are pre-calculating everything and then using the outputs within your evacuation modeling tool. But we know that this is not working well for all possible scenarios, because as I mentioned before, there may be cases in which you are actually interested in seeing what are the inputs, what are the factors that affect the fire modeling from another layer. Think about the example that I did before of the traffic modeling. A traffic model will be able to help you, for instance, to calculate and predict how long will it take, for instance, for firefighter on land to reach a certain area. Well, you cannot do it if you actually source the outputs of the fire model, because you will not be able then to recalculate the evolution of the fire spread based on the intervention of the firefighters. So that's just an example, but in principle, this is one of the decisions that, for instance, those that develop with fire evacuation models like me had to do. Level of granularity also, I mean, this is very much impacted by the scale of the event and the computational time and the scope of what we are doing, because again, if we're using something for real time, we're not going to be able to do CFD calculations in real time. I mean, not going to happen, or faster than real time. Sometimes we actually need faster than real time for evacuation emergency management. So this limits a bit our application. We have ways around it, for instance, to pre-calculate scenarios that are likely to happen, and that's another approach. But and again, going back to what I discussed before, it's a trade-off between the scope of what I'm trying to do, the accuracy of the results that I need, and the computational time that I can afford in a specific type of application. So those are the type of factors to take into account when we evaluate what fire modeling approach is suitable for evacuation modeling applications in the WOI. The other modeling layer is the pedestrian response, and we see that from evacuation response curves that are macroscopic representation, aggregated representation of people response, we can range to much more sophisticated representation. And here I put two figures from two different studies, one from Singh et al. And one from Falk et al. One is a conceptual model of people response based on the protective action decision model by Lindell and Perry, and that's the work from Falk et al. While Singh instead built an actual agent-based model based on the concept of archetypes. This is a very interesting work that has been done. So what he did with his colleagues was to define what are possible typologies of people, archetypes of people in a WOI fire, and then assign certain characteristics and certain responses based on those archetypes. So this is a very interesting approach, which allow us to factor in indeed the specifics of different type of population and different type of people within a household. And as I mentioned before, the more macroscopic approach instead generally takes into account of more aggregated curves of response, which are then distributed along different households. One example, a couple of examples that I put here, there was some work done by one of my colleagues, Rino Lovrelio, that is a massive university in New Zealand. He did quite some interesting work on, for instance, try to implement the factors that affect response and how those contribute to risk perception and in turn affect the different set of actions that people do. So it's a much more refined and detailed representation of individual response and household response. But of course, being much more refined, it needs a lot of more information for calibration. And there is the question, is this needed? Well, it is needed depending on the scope of the analysis that you do, because in some cases, this kind of very detailed representation of household response may get blurry in the scale of the event. In some cases, instead, may have a quite strong impact. Think about a WOI fire evacuation in which there are a critical infrastructure for which we need to really understand what is the individual response of a given building. Think about a hospital, or you might have this kind of events in environments which are very sensitive. Think about if this happens next to a nuclear power plant or things like this. So in that case, we will really want to zoom in on what is the response of that specific critical infrastructure, and then scale it up and see how it goes in the bigger scale. And as mentioned, the work that Lovrelio et al. Did was to indeed link the perceived risk with different internal and external factors characterizing either the household or characterizing the type of threat or social physical environment. So again, this is a much more detailed approach. So the benefits will be a much more accurate representation of the evacuation response at the household level. The main drawback is that this will require much more detailed information about who we are modeling, which may in some case may not be available to us. And again, if we are interested in reading more about this this domain, I recommend a couple of systematic reviews. I have put the list of references at the end of this slide if you want to check how this type of data are collected from interviews, questionnaires, and so on, assessing a real or hypothetical wildfire and WUI scenarios. The other layer that we look at is pedestrian movement. So also here we can range from very simple macroscopic models that look at aggregated movement of group of people to much more detailed microscopic model which look at the individual. So generally those are represented, for instance, with agent-based crowd movement models. And the type of thinking that we need to do is the same. There is not really one approach that this suits all possible application in wildfire evacuation scenarios, but we need to understand what kind of resolution we need based on the data that we have available and on the scope of what we are doing. And when it comes to traffic modeling, we have a classic four-step approach that we'll discuss now, which is helpful to represent the traffic flows along the road network. Also in the literature, also in this case, we find a lot of variability in the resolution and granularity of the approaches that are used. We can range from simple macroscopic traffic flow relationship. Here I put very classic example of what are called sometimes in the literature fundamental diagrams. Some people don't like this terminology because they're not really fundamental, because they can change depending on what kind of conditions are you look at. But those, they basically look at vehicle density and speed, driver speeds, and traffic flows and density, and they represent at the macroscopic level what is the expected traffic flow in a given road segment. And again, those have been very much investigated for the domain of traffic modeling in normal operation. If you have a look at the highway capacity manual, you find very detailed information about this. But for evacuation, they have been explored mostly for events that are not necessarily linked to wildfire. So there is much more literature linked to hurricanes and so on than to wildfires. It's a bit surprising, but the number of studies are much lower when it comes to traffic modeling for wildfires. I mean, we have seen in one of the previous webinar, there was Dr. Wong that presented some of his research in this domain, but there are not so many researchers looking at this worldwide, surprisingly. So how the traffic evacuation modeling will work? Well, you generally have a trip generation stage or travel demand in which you assess the number of trips from or to a particular zone. And in this case, this would be based on household characteristics and how many vehicles are available for each household. Then you have a trip distribution. So you check what are the trips, origins, and destination, and you develop some matrices to actually pair those. And then you have the modal split. So you look basically at what kind of transportation mode is used by evacuees. So if it's a private or public transport, and there are many different modeling approaches for doing this, for instance, based on utility, disutility, like logit models and so on, and different bias factors that can be factored in as well. And then we have the traffic assignment. So basically the route choice in which you have selection of routes between the different origin and destinations. And there are different assumptions that can be done there based on shortest or quickest path, capacities. Recently, we also saw studies linked to familiarity of the routes and so on, congestion. And sometimes when we try to identify optimal condition, we actually study the equilibrium of this, of the system, of the road network system we're investigating. So what we actually need, though, when we study wildfires is those things have to be dynamic, because they probably will change along with evolution of the fire. So we cannot really say people will go from A to B at this time, but we need models that are dynamically take into account of things like what is the likelihood of a household to respond to a given fire, and then down the line be becoming travel demand. What is the dynamic risk distribution? So what are the safe destinations? Do those change over time? Is it a shelter always available as a safe destination, or maybe something that was initially considered a safe destination is not that anymore? And we saw, again, we have seen those kind of scenarios happening in real life. Modal split, as I mentioned before, and also dynamic traffic assignment, considering, for instance, the availability of routes dynamically in relation to the threat evolution. So this is all very important to understand that when we model traffic evacuation in case of wildfires, we need this kind of dynamic approach to account for the evolution of the fire threat. And that's why it's important to have this integrated couple approach with a wildfire modeling tool. And then how this actual coupling can be done to inform decision makers. There are two macro approaches. One is basically using so-called trigger points or trigger buffers. So they use some evacuation trigger points or buffers based on the fire spread modeling or sometimes GIS information. And there is some seminal work done by Tom Kova and some of his collaborators. And more recently, Imperial College, Harry Mitchell did some work on this. Or agent-based approach, so defining rules of communication between the modules. So basically how the different models talk to each other. And there are a few modeling issues there because there could be dynamic elements that need to be represented with given time intervals. You may have counterflows, for instance, for the intervention of firefighters, or simply re-entry, people that decide to change their mind, or they want, rather than going away from the threat, they go towards the threat because maybe they have to fetch family members, or they are at work, they want to go home first, and so on. So the communication between models is still not really fully addressed in the literature. So there is a lot of research to be done in this domain. So this is how it works when it comes to evacuation modeling for wildfires. And here I make you in the last part just an example of what we have developed in this international effort that has been sponsored by NIST, and that involved a few research organizations, as Lund Universities, NRC Canada, Imperial College, the Fire Protection Research Foundation, the NFPA, Movement Strategies, and RMIT in Australia. So what we did was an implementation of a couple fire pedestrian traffic simulation tool through a game engine. So one of those software that I use for developing video games called Unity 3D. That's why it's called Winity. And the idea in this, at the stage of development of the tool, is that we are able to represent the fire spread and have this affecting the pedestrian response, and in turn the pedestrian response affect the traffic, and also the fire also affect the traffic, for instance, by blocking a given destination that is not available anymore for people, and so on, linked to that dynamic concept that I was mentioning before. So when it comes to fire modeling, the first work that we did was to import fire site outputs into Winity. So read basically outputs from an existing fire modeling tool, macroscopic fire modeling tool, so an empirical fire model. We chose this because it was available, freely available, and it was widely used. Now we are moving towards more implementing our own custom cellular automata approach to represent burnt and unburnt area, basically recoding. What we did was to recode behave for the spread rates within Unity. So that's the latest work that we've been doing. Why are we doing this? As mentioned before, because we want to have both modes, external and internal, for fire modeling, because down the line we want to have two-way coupling. So we want to have the traffic model that can affect the fire modeling, because, for instance, we can have firefighting being modeling there, and the impact of firefighting effort on fire spread and so on. But again, this is more of a long-term vision. At this stage, we are just at the stage of developing. Basically, we're not developing a new model. We are recoding existing model behave. Just we set up the rules for the spread rate with the customs cellular automata approach. So basically, cells that are burnt or unburnt based on the spread rates calculated through the approach using behave. So what we do, then we get the fire outputs, and we have some population estimates that we get from a worldwide database called the Gridded Population of the World. And we get an evacuation response curve to represent the response to the fire. So depending on the evolution of the fire, we may decide to have people responding earlier, later, or decided to stay also, a given percentage of people. And then we have some default response curve for each household. That can be, this default can be modified, and people can decide to stay, and the user can modify this. And then we have a simple movement calculation that take into account of possible movement speed of people and their time basically to reach their vehicles. At this point, we're just looking at private vehicles in the Winity. We're not looking at public transport. And then we have implemented a traffic model in Winity, the Lighthill-Witten Richards model, which is a commonly used macroscopic model in the traffic modeling world. And this allows us basically fetching the road network for OpenStreetMap to factor in indeed the pedestrian response, the background traffic, and check the traffic flow in defined locations. So the output of this then becomes the evacuation times, the time that it gets to reach a given area or a given destination. And then we also have implemented, this is the work done by Imperial College. They can surely give you more information about this if you want, a trigger buffer model in Unity, which allows basically to use information from the fire model to estimate trigger buffer considering both fire and evacuation evolution. So basically helping out decision makers in deciding where we should order an evacuation. And the last output that we're able to generate is what we call dynamic vulnerability assessment. So basically we integrate the number of people remaining in the threatened area to in relation to the WR set, the required safe egress time. So we can basically do a dynamic assessment on how many people are left in the threatened area. And basically through this, we can make an assessment of the global community vulnerability. And again, this is a bit different approach than what is done in building fire evacuation, where generally we just look at the final time. But this has much less sense in our case because we have a lot of people that decide to stay. So we want to also know what is the general vulnerability, the global vulnerability that an area has over time. And this is also important because indeed the spatial resolution and the spatial scale that we're looking at may even change over time, because an area that initially will not be possibly threatened may become threatened afterwards. So to conclude this presentation, we need really integrated evacuation models to do a paradigm shift towards vulnerability assessment that is dynamic. So not just looking at the fire risk, but we want to also make sure to know what is the community ability to respond to the risk. Everything that has been done in the domain of evacuation modeling has to take into consideration a stochastic approach, because many of those behavioral elements cannot be predicted with deterministic models. So we cannot be 100% sure of what actually will happen, but we need to set the ground for a stochastic approach so that we can use probabilities of different things to happen. So we will have to use some sort of a Monte Carlo approach to then evaluate the convergence of the different scenarios. And at the moment, what we're doing with Unity, with the Unity team, is also to put together, and this was also a project sponsored by NIST, and we're wrapping up this, a suite of tests for verification and validation that can be used for fire evacuation models. So setting up the grounds for making sure that the basic functionalities needed for fire evacuation are in there. And to do so, we develop ad hoc verification tests for these type of tools, and now we are doing an effort to source data for validation. But of course, validation is never one-time task. We need more data. We need more data about evacuation behavior to calibrate models and validate models. So it is an ongoing effort of I will say of the whole IFSS community to try to source more data from actual events, experiments, or community evacuation drills. So that's pretty much it from my side. So I thank you for your attention. And if you have some questions, please put them in the chat so that I can answer to your questions. We will share the slides later on. Here I put also some slides with references if you want to dig more into certain topics.
Yes, thank you for your presentation, Enrico.
Yes, I stopped sharing.
Yes, and like if you have any questions, please type your questions in the chat. I think it's gonna take a while, maybe like a little bit to put like a questions in the chat box. So I guess I'm gonna ask a couple of questions first. So your team, like a Nifty team, is like developing some site to like solve the like validation. So what kind of like conditions or like when you choose like validation site, what kind of like parameters did you consider especially?
I were to say that unfortunately we don't have too much luxury in having the opportunity to choose where we fetch the data, because very often we have to go with what is available out there. Currently, what we were looking at, and we've also teamed up with another NIST-funded project that is looking at GPS data led by University of Florida. We were looking at the Kincaid fire, for instance, basically looking at large events in which we could get some information concerning the evolution of the evacuation along the traffic network. But this is just one example. For instance, another study that we had the opportunity to do was to actually participate to an actual, observe an actual community evacuation drill that was run in Colorado and in a community called Roxborough Park. And this was through the NFPA Firewise program. You probably are familiar with it. It's a very good program because it encourages community to get prepared for wildfires. And they had actually arranged a community scale drill, which was really impressive. They did really an excellent job because, you know, already to arrange a drill in a building is complicated, but to arrange a building in a community, it entails a lot of effort. And we were given the chance as researchers to observe the actual drill and also collect data. So basically we were looking at, for instance, time to get prepared, so time to actually load your vehicles and proceeding with evacuation, route choice, and different aspects linked to the actual community evacuation. So it was really an excellent opportunity, but I would say that we wish that there would be more communities doing this kind of evacuation drills, because everybody has to win from those. The community wins because they can train for actual evacuation events, and researchers can gain because they can get more understanding about the behavioral aspects that affect evacuation response and then use them for calibrating or validating their models. So that's really an interesting and useful exercise. But at the moment, as I say, we are mostly exploring different avenues. One avenue is the traffic data that can come, for instance, from GPS data. And as mentioned, this team from University of Florida is been very active on this. One avenue that we are exploring within the WNET team has also been fetching traffic data from existing databases from traffic sensors, because many of this information on what is let's say the flows on a road, they are tracked also during normal operations, so we can actually get some useful information there. And another thing that we have started doing that we plan to do even more is using virtual reality experiments, because they allow us to have control conditions. And for instance, here in Lund, we started doing, for instance, simulations of in virtual reality of traffic evacuation in smoke. So, and see how people will drive. So basically the steering wheel, like a video game type steering wheel, and see how people drive when there are reduced visibility conditions due to the wildfire smoke. So in VR, we have much more control on the conditions, but we cannot really rely on only one method, because every method has their limitations. The real data, we cannot really control the conditions. VR is still VR, so it's never the real fire. So we need to always take into account the limitations of using virtual reality. And GPS data, they also have limitations in terms of how much data pins we get. So we don't get everyone on the road. We can use this information, for instance, for route choice, but we don't really have everyone's information of who is evacuating. So the idea is to use different methods to help out with the development and validation of these tools. And our policy is always to put our data in open access. So the community evacuation drill is already in the public report of the WNET report, and also we plan to release the new data that we're collecting from traffic as well in open access, so that other researchers could use it.
Thank you. So Larry asked, is WNET available to be accessed by other researchers?
Yes. So the software is kept by the moment by the Fire Protection Research Foundation, and it is available for everyone. So just drop me an email and I will make sure that you get the source code, possibly the source code, but for sure you will get a freeware version of the tool. Now we are actually working towards actually releasing the source code as well, but at the moment we have basically a freeware tool standalone that you can play with. The only thing that we request for whoever works with WNET is that whatever you do, in terms of development will have to be released for everyone as well, so that the whole community benefits. So we will put it open, and we expect everyone to put it open as well. That's a bit the only request that we have for users, for developers, because if you're simple users, no, then you can just try it out. And of course, it's not a commercial tool, it's a research tool that we are developing, so you have to be let's say, it's your own responsibility of the use that you do it. But yeah, it's available. So if anyone is interested in trying out, please drop an email, and I will make sure to give you the software.
That's nice. That's really nice. So there is like a large question. So yeah, hi Nico. Sorry I missed the first 10 minutes of your webinar. If you covered this in the first minutes, I will look at the slide and it's like, okay. How have you gone about developing synthetic populations that simulate the location of agents throughout the 24-hour period, so that at the point of evacuation decision being made, there's a population in homes, business, on roads, at parks, on the bench, etc.?
Yeah, so that's a good question. So what we do is that technically we can start the simulation at any point in time that we want. So we don't have to necessarily, actually we don't start the simulation when the evacuation starts, but we start before. So what we do is that we assign population when we start the simulation in the household, but not only. We also assign criteria for so-called background traffic, because we know that the background traffic can have an impact on the road capacity. So that's also an input of the model, because, you know, if we have an area in which we know that there is background traffic, that is likely to reduce the capacity of the road and then increase the evacuation time. So what it actually is done is that the model will actually be run before the actual evacuation order. You will have the people assigned in the households with a given evacuation response based on all these factors that I described before. And then we will see how you are able to see how the evolution of the evacuations versus the fire interact with each other. So basically, the fire simulation is going on. You see where the fire front and where the fire spread is going, and basically then you have an information about how many people are still on the road or on their households during the course of the simulation. So we actually give this. That's why we don't just look at the evacuation time as mentioned before, but we look at this vulnerability assessment, which is basically an indication of how many people you have left in the threatened area. So that's why we don't just look at the classic require egress is safe time, but we also look at how many people we have left in the area.
So one more small question and then wrap it up. How do you get the data for background traffic at the local, regional, like the state scale?
Well, there are some databases that actually provide this type of information for given roads. For instance, really now we are working with a database from Caltrans, the Californian Transportation Department, that provide the information for the train traffic. So there are databases worldwide that provide you this type of information. And you know, when you look at traffic data, it's never flat. So you have like day, night, and you also have weekend peak. So you also need to then be sure to check what is the time of the day in which in the given scenario in which you are actually having this evacuation scenario, because even under the very same conditions, if the fire is a day or a night, it's a completely different starting point, if you know what I mean. But there are databases that come from the regular traffic routine world that provide this type of information. As I say, right now we're actually working fetching data from one of the databases from California Department of Transportation.
Okay, thank you. Like now it's 1 hour is past, so like we thank like Enrico again for the webinar, and thank you everybody for joining this webinar.